So here's an example that's a little bit different. Here they're asking us to write the node equations and auxiliary equations if needed, so that we can solve for all the voltages in these networks. And they want to do it in terms of the components, so the resistances, the capacitance, and all that. But they don't want us to solve for these, and they just want us to set up the equations. So to do that, or before we do that, we need to recall, since we're doing nodal analysis, that's where we sum all of the currents leaving and entering a node. So since we have nonlinear components, we need to make sure we can recall how to express that current. So of course, if we have a resistor, that's easy enough, right? That's just Ohm's law, simple application of the voltage over the resistance. Next, if we have a capacitance, recall there that I is equal to the capacitance times the derivative of the voltage with respect to time. And then if we have an inductance, current in that case is equal to 1 over the inductance times the integral from 0 to t, some time frame, of the voltage with respect to time. So keeping those in mind, let's see if we can go ahead and work this out. So we'll look at circuit A first, and let's go ahead and designate that. And so in this case, we want to consider this node here, node 2. And so let's sum up all the currents going in and out of there. So when we do that, the first thing we note is we have this capacitance right here. So using that equation we have above, that should be pretty simple then, right? That's just going to be the capacitance times the time derivative, dt of the difference in the voltages. So it's V2 minus VA. So that's the expression for the current from the capacitance. Moving down the line, we see that we have this dependent current source. We can write that one just as it is, right? And it's showing it entering the node, whereas typically we consider leaving the node as positive. So that'll be a minus K Vx. Next, we have this inductor, L1. So if we write that, that's going to be plus 1 over L1 times the integral of V2 from 0 to t dt. And then finally, we have, we'll just go back to red, we have this resistor right here, and that is just the simple application of V2 minus V3 over R2. And we said all of this, that's all the nodes, or all the branches going out of node 2, set all of that equal to 0. So in order to solve this, we don't have quite enough information, so we need to keep going. So now we need to go to node 3. So if we go to node 3, that would be this node, that would be this node here, node 3. And so let's do summation for that, or all the currents going in and out of there. So mark that as green. So we know we already got R2, and so that's just going to be equal to V3 minus V2 over R2. Next, we have this inductance. So in that case, that's going to be plus 1 over L2 times the integral of V3 from 0 to t dt. And then finally, we have, I'll do it in purple. We have this Vx, our resistor R1, which defines Vx. And so in that case, that's going to be V3 minus V1. You could also say it's VA, because VA is driving that node, so VA. So V1 or VA is correct, over R1. And so that's all the branches going in and out of that node, so that'll be equal to 0. So these are the two node equations that we have. So we need one more auxiliary equation that relates Vx to the other voltages. And so to get that, we can consider this path here in yellow. And so there, we can sum those up. And so when we do, what we would have then is VA plus Vx minus V3 should be equal to 0. Okay. So that's the A circuit. So now we can look at the B circuit. So let's draw a dividing line here. It's the same type approach though. So if we, again, this is the B circuit. So on this one, again, we're going to look at node 2, which is here. Oops, sorry. Use my highlighter. Node 2, which is here. And so as we do that one, let's go around and see what we find. So the first thing we see is this capacitance. And so we can write that then as C times the time derivative of V2 minus, we could say V1 or VA. Both are correct. So we'll say VA to relate it to a component. And then as we move around, we see this branch here. It's just a current source, and it's just I, and it's entering, so that'll make it negative, so minus I. Simple enough. Moving around, we see we have R1. So to account for the voltages across that, we have to take in that dependent source. So that's going to look like V2 minus K Vx minus Vx all over R1. And then that's all the branches for node 2. So then we can set that equal to 0. Next, we want to look at node 4. So we'll put that right here. So node 4, as we go around that one, first thing we see is this R2. And so that's a simple Ohm's law. So that's just going to be V4 over R2. And next we've got that R1 in green, so we can apply the same way. So that's going to be V4 minus, or plus this time, KVX minus V2. That's because of the sign notation on there, our convention. That's all over R1. And then finally, we've got this inductor here, L. And so if we write for that one, it's going to be plus 1 over L, integral from 0 to T. And this total voltage on that one then is V4 minus VBA, or VB minus VA dt. And and that's all equal to 0. So the one thing we do need to note here then is that Vx is also equal to V4. So everywhere you see a V4, you could put the Vx into that, which will help to solve those equations. But that should be all you need to solve for those. So again, just a quick exercise to show how things are set up, especially if you have a little more complicated circuit with some nonlinear devices.